Hello again, it's Chris Thompson, NASA Solar System Ambassador, here with a presentation on meteorites. I've taken some material from NASA and the Meteorite Association of Georgia to put together a brief presentation as an introduction to meteorites. So we'll start with a few things that are not meteorites: comets and asteroids. These are both things from which meteorites come, but they're not meteorites themselves. So comets, as Carl Sagan described them, are dirty snowballs. They're in highly elliptical orbits, made mostly of ice but with rock on sprinkled throughout them, and they orbit from very close to the sun to very, very far away from the sun, sometimes even outside of our solar system. And they leave behind a trail of debris in their tails that the Earth can sometimes plow through, and that's where we get regular meteor showers from. The same thing is true with asteroids. However, asteroids are more like a icy dirt ball, to turn Carl Sagan's analogy around. Asteroids are rockier with small amounts of ice. They're located mainly in orbits more circular and located between Mars and Jupiter in the main asteroid belt, but they can be anywhere and they can have highly elliptical orbits. But they're generally rounder objects. They're generally in more circular orbits, and as you'll see from this photograph of the asteroid Bennu, very dark in color. And in fact, we expect that Bennu will turn out to be one of the darkest objects in the solar system when our samples from OSIRIS-REx get back. We expect it to be a carbonaceous chondrite. We know it has a very low reflectivity, and this is a good photograph of the asteroid itself. We'll be checking out more with Bennu during the course of 2020, and I'll do some videos on the OSIRIS-REx mission itself. But asteroids are the most numerous small body in our solar system. They represent the #1 class of objects of small size. Those asteroids are near-Earth asteroids, which means that they're closer than 1.3 astronomical units from the sun. That's about 120 million miles, or if you want to think about it, for the distance to the Earth to the Moon, about 500 times the distance from the Earth to the Moon. Anything closer than that is considered a near-Earth object. And then there's potentially hazardous asteroids, and those are the ones that cross the Earth's path. So if it's a potentially hazardous asteroid, it's one which could actually impact the Earth. Hopefully we get meteorites from it and not like something that wiped out the dinosaurs. An asteroid discovery timeline here shows an animation by Scott Manley that runs from 1980 to 2010, and it shows the discovery of about 500,000 asteroids. As they're discovered, they turn white. Then they're color-coded. If it's green, it's in a stable orbit, not coming close to the Earth. If it's yellow, it's one of those near-Earth ones. And if it's red, it's a potentially hazardous asteroid. So by far, the vast majority of these asteroids are green. They're not going to come near the Earth. But there are a few that could come close to the Earth, or that do come close to the Earth, and there's some that will eventually strike the Earth. Now, those will give us meteorites, and hopefully not wipe out anything. We don't know of anything that's really large that's headed our way. So we'll keep an eye on that and let everybody know if there's something new coming our way. Meteors themselves are the leftover bits and pieces of small bodies that are coming through our atmosphere. They are coming in generally very high, very fast, anywhere from 25,000 to about 150,000 miles an hour. They are going so fast that when they strike the atmosphere, they'll actually ionize the atmosphere and give a characteristic glow around the object. So what's burning is really the atmosphere. The objects that come in are generally no larger than a grain of sand, and they'll burn up long before they come to the ground. So it has to be a fairly large object, maybe the size of a basketball, beach ball, or even larger, before it will provide enough material that will make something solid all the way to the ground and give us a meteorite. But these objects begin to burn up about 75 to 50 miles into the atmosphere, and then they end up stopping to glow about 10 miles above the atmosphere. So they only glow during the top part of that flight when they're going very fast. As they slow down, they ionize the atmosphere less and eventually go into what we call dark flight. And if there's anything left over when it gets to about 10 miles, that itself will fall to the ground. Now, what it would look like if it was burning through the atmosphere is this. It's a fireball coming in, and as it breaks up, that's when we get excited. We might see some meteorite pieces landing from a fireball. The history of meteorites goes back about 4.5 billion years to the very beginning of our solar system. long before there was a sun, there was a nebula, a gas cloud that had gas and dust in it that began to collapse under its own weight. As it did so, the sun was formed about 4.5 billion years ago, and the leftover material that was still in orbit, circling around the sun, formed what would then become protoplanets, asteroids, micrometeoroids, and as those little bits of matter came together and formed, they were very tiny at the very beginning, and as they formed, they would then do what's called accretion. As little bits of matter formed and then stuck together, you get bigger and bigger pieces that grew, as I mentioned, from asteroids, micrometeoroids to protoplanets, and then beyond that, as they got larger, they actually had enough gravity to begin to collapse themselves and then heat up and eventually metamorphosize into one solid rock. So they go from a rock pile, a rubble pile, to one solid object, and as it got heavier and heavier and had more pressure, it would also differentiate. So the oldest material never changed from the very beginning of the solar system. The younger materials differentiated, and you have all of that rock and metal that was together in the oldest pieces begins to separate out as it differentiates, so that the core of a large body is all iron and nickel, and the crust is mainly rock. Very little iron or nickel is left at the top surfaces of these larger bodies like the Earth. Stony meteorites come from those very old material. You see stone and iron mixed together. You see the individual chondrules before they were metamorphosized, before they were differentiated and destroyed. You can actually see that. So we know that the stony meteorites are some of the oldest meteorites that we see. So if you can still see the chondrules in them, they are very old. Iron meteorites, on the other hand, this one has been cut and etched to show a very characteristic pattern that gives away its meteoritic nature. So we know a piece of earth metal won't have this pattern, and when people ask us to classify meteorites, if it's an iron meteorite, we'll cut and etch the surface to verify if it is in fact a meteorite or if it's a piece of earth metal. So these iron meteorites, examples would include Canyon Diablo from the western United States, or Sokotia from Russia. There are lots of other metal meteorites that are very prominent. In fact, the largest in the world is called Hoba, and it is in Africa. So there's an example of an iron meteorite. A stony iron meteorite has both elements to it. In this photograph, you see what looks like white is actually silver, and that's the metal part. And then there are crystals of olivine. If you're a gemologist, you might recognize it as peridot, the birthstone for August. But in this case, we call that olivine. If you cut a stony iron meteorite very thin, on the order of a millimeter thick slice, you can actually pass light right through it, and it looks like nature's stained glass windows. So they're very beautiful and very rare. A carbonaceous chondrite is a different type of chondrite. It is mostly carbon, very dark in material, very friable, in other words, fragile, and will break apart very easily. But in this example, if you look at the photograph, there's some splotchy white areas, not the round parts, but the splotchy white areas. There are calcium aluminum inclusions, and those are the oldest solid matter in the universe. Those are parts of the material from that original nebula that condensed out first. So they formed solid matter first, then the other material gathered around that. Those are accompanied in some cases by what we call pre-solar grains. Those would be solids that predated the universe, so they were actually solid pieces in that solar nebula that formed the sun. Those are very exciting to find, very rare, but very important for scientists to understand the origin of our solar system and the origin of the universe itself. Now, getting back to the ordinary chondrites, you see in this photograph an ordinary chondrite cut thin. You can see the white speckles on it. Those are the parts where the metal is reflecting the light, so you can see it's both rock and metal all mixed in together. A very old kind of meteorite, and different from this next one, which is called an achondrite. An achondrite came from a differentiated body where all the metal had sunk to the center of the body and leaving the rocky material at the surface. So the chondrules were destroyed. The material is very metal poor, so it's almost all rock, very little metals left in it, and that's an achondrite. That's exciting for planetary geologists to find because Sometimes those achondrites come from very large bodies. We'll see more about those in just a second. We find meteorites on Earth in places like Antarctica. It's very cold and in fact very dry there. It's so cold it doesn't provide liquid water which would then weather the meteorites. It preserves them in this very frozen wasteland, and Antarctica does us a favor as well. The continent ice sheets are moving, and they're moving towards the mountain ranges in some cases. As they move towards the mountain ranges, the ice and snow sublimates in the windy Arctic or Antarctic weather, leaving the rocks behind. So it kind of provides a conveyor belt, if you will, where scientists go down there about 6 months out of the year, the sunny months, and they will hunt meteorites right on the surface of the ice. So it's a very challenging job to be down there, not in great conditions. You're out in tents on snowmobiles for hours and hours every single day, hunting meteorites in well below zero temperatures, and they gather hundreds of pounds of meteorites on an annual basis and bring them back to study for science. We also find meteorites in deserts. In this case, it's Meteor Crater in Arizona, or Beringer Crater, just south of Winslow, Arizona. That crater is about 1 kilometer across and over 500 feet deep. And the actual floor of the crater you see in the photograph is really not the bottom of the crater. When that was excavated about 50,000 years ago by a giant metal meteorite smashing into the ground in Arizona, it ejected tons of material. And some of that material actually fell right back inside the crater itself. So the crater is much deeper than what we see because the material that fell into the crater came out of that hole to begin with. You get an estimate of the size. You can see the road driving up to the edge of the crater. There's a visitor center there and a museum which houses the largest single piece of the Canyon Diablo meteorite, which would fit on the size of a table. So it's not a very big piece left over from what struck the ground originally. There are other meteor craters on Earth. Many of those get weathered and disappear over time, but large ones like the top two on the left are from Canada and on the order of 60 miles across, down to the one on the bottom right, which is in Egypt, and that one you can see the people in it. So there are very large craters, there are very small craters, but on Earth the weather tends to make those disappear. A place where meteor craters are preserved is the moon. On the right you see a before and after photograph, and on the left it toggles back and forth between them. In March of 2013, about a basketball or beach volleyball size meteorite struck the moon and left about a 20-meter crater. So very large crater for such a small object, indicating a very quick, very fast passage, and with no atmosphere to slow it down. The big rock hits the moon's surface and makes quite a big hole. In fact, a long time ago, some of the largest impacts could have struck the moon, or did strike the moon, with enough force to knock pieces of the moon off and allow them to escape the moon's gravity. And when that happens, we can get meteorites from the moon that land on the Earth. So you can't own a piece of the Apollo program moon rock that was brought back by the astronauts, but it is possible for people to purchase meteorites that came from the moon. And we can classify those as their origin from the moon by knowing the samples we got from the moon and comparing those to the samples that we've received in meteorites, do a chemical analysis on both. If they match up, it's like a fingerprint. So we can tell where meteorites came from if we have a known sample. There's only a couple places where we have that. The moon is one, and Mars is another. So we've been to Mars with spacecraft that have analyzed rocks and atmospheric gases on Mars, and we found the same signatures in meteorites that we found on Earth. So we know these meteorites come from Mars. The one in the photograph is one that was picked up in Antarctica. There are others. We'll get a closer look at those in a future video. These two videos here are about the Chelyabinsk meteor, and it's coming in. It was actually brighter than the sun as it broke apart when it detonated in the upper atmosphere. People weren't injured by the meteorite itself. What happened was people went to the windows when they saw this brilliant light, and as they were watching that light, the shock wave as it went from supersonic through the sound barrier, it sent out a large, very, very strong shock wave that took minutes to get to the ground because it was so high when it went through that sound barrier. But that shock wave broke windows, and the people that were injured were generally injured by flying glass. So you see a big meteor going through the atmosphere, go outside. Don't look at it through a glass window, because that shock wave is going to make it to the ground. So that's our overview of meteorites. We'll give a future presentation on each of the different kinds of meteorites, and if we have questions from the comment area, we'd be happy to answer them. Thank you for your time.